So differential equations. We understand that differential equation is an equation that involves one or more derivatives of an unknown function. So when we take an example y is equal to 3x squared plus 4. We understand that the y is our unknown, and then the x is our known. Therefore, the y depends on the x value. So when we know the x value, we can easily find the y value. So that is what we mean by an unknown variable. And then we know that as per the definition of a differential equation, it's an equation that's a differential equation. Differential equation is an equation with an unknown y together with either one or more of its derivatives. Here I mean the y, the x, it could be the squared y by the x squared. That's y prime prime. So when we take an example of a differential equation is the squared w over the x squared minus x w dw plus w is equal to 0. This particular equation is a differential equation because we have the derivative of the unknown function, which is w, with respect to the known, which is x, and then we have the dw, that's we have w and then the w being the unknown function. So you could see that in this particular equation, when you say equation x, we have the unknown function w, and then we have the derivative of the unknown function, that is the d squared w with respect to the known. So this particular equation qualifies to become a differential equation. So we actually have two types of differential equation. Talking about types, we have the ordinary ordinary differential equation, here represented by dE, and we have the partial differential equation. That's when we are grouping them with respect to types. So with the ordinary differential equation, it actually has a single independent variable. I've already explained what an independent variable is. So we take this example, an example dy dx is equal to 3x. This particular equation, this particular equation, this particular equation is an ordinary differential equation because we already have one unknown. But then when we talk of partial differential equation, then we have more than one unknowns, changing more than one, I mean, known variable with more than one unknown. An example here is the squared y over so an example here is the d squared y over the x squared plus the y over the v. So when we look at this example, we can see that we have the unknown variable being y, but the number of known variables are 2, which is x, that's x, and then v. So y is the unknown, unknown variable, and then x and then v are the known variable. So in this instance, we call this a partial differential equation. So we are moving on straight away to linearity, grouping differential equation with respect to linearity. So in terms of linearity, we have three conditions that have to be met. And one of them is that the differential equation, that is the derivative of the differential equation together with the unknown variable itself, should have an order of 1 or should be to the first power. So here, the unknown variable together with its derivative, that is y prime, it could be y prime prime, should all have a power of 1. So for a differential equation to be linear, the unknown variable y should have a power of 1. The unknown variable both, derivative, that's y prime, should also have a power of 1. That's the first condition. So now the second condition is that there shouldn't be nothing like the multiplication as the product of the unknown variable with its derivative. So such a thing is actually, not allowed. The multiplication of y, that is the dependent variable, by its derivative. Such a thing shouldn't happen. When it happens, we disqualify it from being a linear equation. So we move on to the third condition. The third condition is that there shouldn't be anything like transcendental function. With the argument being the dependent variable. So what this clearly mean is that there shouldn't be an equation where we have cos y, with y being the dependent variable, or something like an exponential function, that is e to the power y or ln y. You could see that the argument here is y. When that happens, we cannot call the equation linear. So this one in particular too is prohibited if we want to have a linear differential equation. So now that we have spelled out the three conditions, I would quickly give an example. So we look at this example. An example: dy dx raised to the power 2 plus dy is equal to 0. So now we want to find out whether this differential equation is linear or not. And we can recall that the first three conditions is that the unknown variable together with its derivative must all be to the power 1. That's spelled out at the first condition. That's y together with y prime prime should all have a power of 1. But in this example, we can see that dy dx, which is y prime, is to the power 2. And clearly, you can see it disqualifies it from being a linear differential equation. So this particular one fails to be a linear, differential equation. Also, we can group differential equations in terms of the degree. So, degree, classifying differential equation in terms of the degree. And also, the degree here talks about the power, that is the power of the highest derivative of the highest derivative. But then there are conditions to be met. Let's spell out those conditions. So the condition is that the differential equation should be a polynomial of its derivatives. And so the differential equation should be a polynomial of of its derivatives. So what that simply means is that we have next example. An example is that y prime prime plus k ky squared is equal to 0. So now the degree is simply the power of the highest derivative. And so we can find out that in this particular differential equation, there is only one, there's only one derivative, that is the y prime prime, and that happens to be the highest derivative. So here, if we are in for the degree, then that should be the power of the y prime prime, y prime prime. So we can see that that one is clearly 1 because the power of this y prime prime is 1. Therefore, degree of this particular solution differential equation is 1. So degree is 1. Why? Because it is clearly in a polynomial form. You could see this is more or less like, I mean, a quadratic equation. It is in a polynomial form. Therefore, it satisfies the condition. Alright, so we take a second example on the degree. So, example 2. Example 2. Here we have dy x plus sine dy dx is equal to 0. So now we want to define the degree of this differential equation. Now we have to go back to our condition. The condition is that the differential equation should be a polynomial of its derivative. So here we have y prime. Rewriting, so we have y prime plus sine y prime is equal to 0. Now, you can see we have a transcendental function here with the argument being y prime, and that is actually the derivative. This is the derivative of the dependent variable. And remember that when we're talking about linearity, a differential equation fails to become linear if the argument is the dependent variable. That's when we have a transcendental function. So this presents the argument being y fails to make this particular equation a polynomial of its derivative, in the sense that if we had y prime plus sine x is equal to 0, then this particular equation is a polynomial, that is in terms of its derivative, because the argument is not the dependent variable. Therefore, it is still a polynomial. So this is a polynomial. But in this case, since we have the argument being the derivative of the dependent variable, this one is not a polynomial. So now that we have clearly, understood what it is for a differential equation to be a polynomial, then we can continue solving our problem. So we now understand that this is not a polynomial. Therefore, our degree So the degree of this differential equation, that is the y, the x plus sine the y, the x is 0. That is degree is undefined. Degree is undefined because it fails to be a polynomial in terms of its derivative. So now we move on to solutions to differential equation. That is solutions to differential equations. So now the solution to differential equation are functions. That is the solution to differential equation represented by dE are functions. We have to take note of this. They are not numbers. So here I'll be taking one example. So let me say we have this differential equation y x is equal to c1. I mean this c1 cos x plus c2 sine x, with c1 and then c2 being the arbitrary constants. So this is a differential equation, that is c1, I mean cos x. It's actually the general solution because of the constant c. These are general solution to a differential equation I'll be giving. So this is the differential equation d squared y over dx squared plus y is equal to 0. And then the question is that we should prove that the general solution, that is, let me say x or star, this particular solution is the solution to this differential equation. Let me say star star. So that's what we are going to show. Our aim is to prove that. And in proving that, we take our differential equation, that is this the squared y over the x squared plus y is equal to 0. And then we have y x is equal to c1 cos x plus c2 sine x. So what we are going to do is that when we take the differential equation, we have to differentiate twice because we have it in terms of, we have the squared y, over the x squared. I mean, this means we have to differentiate twice. So wherever we come across the squared y, we put in the differentiated value of the yx, and whenever we see y, we put in our y value as the yx. So we differentiate twice. So in differentiating y x, that's y prime, we get, in differentiating cos, we get negative sign. So we get negative c1 sine x. And when we differentiate side, we get cos. So plus c2 cos x. Now we find y prime prime of x, and that will be negative c1 cos x minus c2 sine x. So this is what we have as our y prime prime. So now we substitute these two, okay, that's equation 1 and equation 2, back into the differential equation up here. So now we have the squared y over the x. There we put our as negative c1 cos x minus c2 sine x and plus y. Now we understand that y is the c1 cos x, as we can see here. Our y is the c1 cos x plus c2 sine x. So we come and add that. So plus c1 cos x plus c2 sine x. And here we could see that the left hand side is 0. I mean this one cancels this. This one also cancels this. So we have 0 being our final answer. And we could see that it satisfies the equation right here, the d squared y over the x squared plus y is equal to 0. Now we can see that we have 0 as our final answer. Therefore, it is indeed a solution. Therefore, the general solution given as yx, this particular one, is a solution to the differential equation star star. So now we move on to first order. We move on to first order differential equation. First order differential equation. So with the first order, there are several first order differential equation. As the name suggests, it's of first order, meaning the degree is 1. The degree of y together with y prime y prime is 1. Yes. So that's what we mean by a first order, and it's actually of the form dy dt plus pty is equal to gt. So anytime we come across a differential equation of this format, then we know it is a first order in the sense that the degree of the derivative is 1, right? So this is a first order differential equation. Now there are several methods of solving for the general solution of first order, and one of them is the integrating factors. That's the method of integrating factors. So we are touching on method of integrating factors. So for the method of integrating factors, the differential equation, we know it's of first order already, should be of the form dy dt plus pty is equal to gt. So in solving, we look for our coefficients, our integrating factors. Yes. But before that, the coefficient of the dy dt should be 1. So coefficient of dy dt should be 1, must be 1. So when we satisfy all of these conditions, then we move ahead to look for our integrating factor. And we know that our integrating factor is represented by mu of t, and that should be equal to e raised to the power the integral of d vein d 0.196 vein. So this is our differential equation, and we can see that it's of first order because the highest derivative is the pt as of the first derivative. So as the first order differential equation. So in solving this, so now before that we write our differential equation. We write it dividing the t minus. So we move, transpose this one from here to the left hand side so that it becomes plus 0.196 Vim is equal to 9.8. So now we compare, we have it as compared to the form to which it should be. We have dy dt plus pt y is equal to j t. So now we could see that we have it in this form. There's some relation. So now that we have it that way, we can see that our pt is equal to 0.196. So now we can find our mu of t. And mu of t is e to the power integral of pt here becomes 0.196 dt. So when we integrate this, what we get is we get e to the power 0.196 integral of 1 integral of 1 dt could be, that's integral of dt, and finalizing this gives us e to the power 0.196 t. So this is our integrating factor. So after finding the integrating factor, we multiply through the whole equation with our integrating factor. So now we have the differential equation dv dt multiplying the integrating factor e to the power 0.196 t plus 0.196 v multiplying the integrating factor e to the power 0.196 t should be equal to the right hand side 9.8 times e to the power 0.196 t. So now here's something we should take note of. After multiplying through, you get to a point where your left hand side becomes the product of your dependent variable, that is y, times your mu of t. It becomes this, or prime. Yes. So this is what you get for the left hand side. So this actually, characteristics we should take note of. It's a property we must take note of. That after multiplying through with your integrating factor, your left hand side becomes, that is the dependent variable times the integrating factor, or prime. So now we can move ahead and compute. So this is what we get for our left hand side. So we get left hand side, we know should be y times mu y, but in this case our y here is vin. So we get the left hand side to be vin times our mu of our integrating factor, which is e to the power 0.196 t, or prime, should be equal to the right hand side. And what did we get for the right hand side? We had 9.8, that is equal to 9.8 e to the power 0.196 t. So this is an equation where we can easily simplify. So here we do our integration, we bring our integral sign, and because of the prime here, the integral sign takes away the prime, So what we get now is v multiplying e to the power 0.196t is equal to the integral of this. And since 9.8 is a constant, we bring it out. So 9.8 integral of e to the power 0.196t. So we get the right hand side as v multiplying e to the power 0.196t is equal to 9.8 over 9.8 over 0.196 plus, that is, sorry, e to the power 0.196 t plus c. Yeah, so this is what we get our proceeding answer. And in doing so, comes the point where v to the power e 0.196t is equal to, now we know that 9.8 over 0.196 should give us 50. We get 50 e to the power 0.196t plus c. But then our aim is to solve for v. So we divide through by e to the power 0.196t, divide e to the power 0.196t, and divide through by e to the power 0.196t. So we know that this one takes away that, and this one takes away that. So what we come to have for our final answer is that v is equal to 50 plus c e to the power negative 0.196t. And you could see that we have this as our general solution because we have c there. So this is our general solution. The general solution go ahead to tell that it is a first order differential equation because you only have one arbitrary constant. You only have one arbitrary constant, meaning that it was truly a first order differential equation. So that is for the integrating factors. So quickly we move on to the Bernoulli equation. As Bernoulli's equation. So Bernoulli is used to solve first order but non-linear differential equation. So the equation should be of first order, but then it is non-linear. And what accounts for the non-linearity? The non-linearity, that's non-linearity is as a result of the degree of the dependent variable. So a degree of the dependent variable here, y. So meaning y is the power n, where n is not equal to 0, neither is it equal to 1. So this is the condition. So any time that we have a differential equation where it is of first order but then it's not linear, and the non-linearity is as a result of the degree of the y, then that is a Bernoulli equation. So the Bernoulli equation is of the Bernoulli equations of this form. So it's of the form y prime. So y prime plus pty is equal to kill t, that's y to the power n, where n, as stated earlier, is not equal to 0, neither is it equal to 1. So now, how do we go about this? Bernoulli says that when you have such a differential equation, what you do is to divide through by, so divide through by y to the power n. So that's what we do in the first place. So here what we come to have is that after dividing through by y to the power n, then you make a substitution. Yeah, we effect a substitution, that's z. Let's make z, say z is equal to as y. All right, let me take an example so that we can appreciate that better. Yes. So an example. So let me say we have this example y prime plus 4 on ty is equal to t to the power 3y squared. So let's do a quick examination. This is of first order because the degree of the, we could see that it's of first order. Yeah, it's a first order differential equation because we only have y prime, that's the first derivative. But then this equation is not linear. And the non-linearity is as a result of the y squared. The y squared. Therefore, this is a Bernoulli equation. So what we do is that divide through by y squared. So when we divide through by y squared, we come to have y prime over y squared plus 4 on t y. I mean, that's y to the power negative 1 because I've divided through, and I get t to the power 3, and y squared cancels y squared. So we get this equation. So when we get this equation, Bernoulli says we effect a substitution. But before that, we could rewrite this equation in this format. So we have y, that's y prime, times y to the power negative 2 plus 4 on ty to the power negative 1 is equal to t to the power 3. So now Bernoulli says we do this, let z be equal to the coefficient of this particular, expression. So z becomes the y coefficient, that's y to the power negative 1 of this particular expression. And Bernoulli says that you go ahead and differentiate this z. So now this z is differentiated, we get z prime, and then we get negative y to the power negative 2. So after getting this into 1 and then 2, we come and then substitute them into the equation. Wherever we see, the y to the power negative 1, we put in z. But mind you, we don't just differentiate the z, we differentiate the z implicitly. So in differentiating this particular z, we come to get negative y to the power negative 2 times y prime, because we differentiated implicitly. So it becomes this way. And from here, we make y prime the subject. So y prime becomes z prime, or z prime over, so z prime over negative y to the power negative 2. So let me call this equation 3. Wherever we see anyone that we can substitute in our equation and we should effect that substitution. So now let's take our differential equation once again. So we now have y prime multiplying y to the power negative 2 plus 4 on t y to the power negative 1 is equal to t cube. So when we do the substitution, we understand that we get y prime. In place of y prime, we put, our, in place of y prime, we put z to the power, that's prime, z prime over negative y. We get this. And that is multiplying plus y to the power negative 2 plus 4 on t. And in place of y to the power negative 1, we put our z is equal to t. So here we could see that this one takes away that. So we come to a point where we have negative z prime plus 4 on t, z is equal to t to the power 3. T to the power 3. So this becomes our equation 4. But you can clearly see that this equation is the first order equation, that is z is to the power prime, so z prime. So the first order equation, differential equation, and then you can see that it is linear. So this equation is linear because the power of the dependence is to the power 1. This equation is linear. So it's now linear differential equation. So we have graduated to the point where we can use the integrating factors. So we solve this equation with the integrating factors. So now we understand that this particular equation can be solved with the method of integrating factor. We just walk through the example, the method we solved earlier by finding our integrating factor and then multiplying through, and we solve for our final answer. So I'll be touching on the next method, that is the separable differential equation. So separable differential equation. So here it doesn't matter whether it is linear or non-linear. So it could be linear or non-linear. It doesn't matter. It matters when we can separate the differential equation. So an example is here, where we have the dy dx is equal to x squared all over 1 plus y squared. So this particular equation is not a linear differential equation. But then you could see we can effect, some separation. We can separate the y values and we can separate the y values and separate the x values. Yes. So let's effect that, separation. So we come to a point where we have 1 plus y squared y is equal to x squared dx. We just did a cross multiplication and we had this. So you can see we now have separated the x and y values. So now we quickly do our integration. So integral of this expression and then integral of this expression. So we get integral of dy plus integral of y squared dy is equal to integral of x squared dx. So in solving for this, we know that it's a constant here y, so we get y plus y to the power 3 on 3. We ignore the c is equal to x to the power 3 on 3. We could choose to bring the c here because it's an arbitrary constant. So now we have this as our expression, and you could see that the differential equation has been solved. So I can choose to make y the subject by y is equal to x to the power 3 on 3 minus y to the power 3 on 3 plus c. And this becomes my general solution. So this is my general solution. So the method of separable differential equation, or the method of separation, is that simple. It's careless as to whether it is linear or non-linear. What really matters is that the differential equation can be separated. So sometimes you have a differential equation where the method of integrating factors cannot solve, the Bernoulli fails to solve for us, then we consider the separable type. If it can be separated, then that's fine. If it cannot, then we look at non-separable. So we look at non-separable differential equation. So we have this as our next subtopic. So when a differential equation is non-separable, then it could be one, homogeneous, or two, non-homogeneous. That's non-homogeneous differential equation. So quickly, we'll be looking at homogeneous. So homogeneous differential equation. Mind you, we are under non-separable. So we are under non-separable. This differential equation is not separable. So number one is homogeneous. So a differential equation is said to be homogeneous when we say we have this expression, the function f, where f lambda of x, comma, f lambda of y is equal to a common expression where we have lambda to the power n, that is multiplying fn, sorry, fx, that's the equation fx, and then y. So a differential equation is homogeneous when we have the expression f lambda of x, comma lambda of y is equal to lambda to a common power multiplying the f of x. So quickly, an example is taken. And an easy way to also find out whether a differential equation is homogeneous is this. So let me take this example. Example is x squared plus y squared. Let's solve to see, is it homogeneous? Is it homogeneous? So now what we do is that we have, in place of x, we put lambda x, and in place of y, we put lambda y, and see whether we can meet this condition. So we have it as x, as lambda x squared plus lambda y squared. And what do we get for this? We get lambda squared x squared plus lambda squared y squared. And you could clearly see that this can be written as lambda squared x squared plus y squared. That's when we factorize the lambda squared out. So we can clearly see that this is equal to, when we put the lambda in there, right? So we now meet our condition as f x lambda of x lambda of y is now equal to lambda to a common power x y. So we could see that it meets. So it means showing that this particular differential equation is homogeneous because n is 2 here and lambda has been factorized. Therefore, this particular equation is homogeneous. So when you have a homogeneous differential equation, how do you solve to get your general solution? But mind you, this equation is not separable. So we introduce two substitutions where we have y is equal to x and then we integrate y. So dy dx should be equal to integrating this, differentiating this, we get v, that's by the product rule, we differentiate, we take v and then keep v as a constant and differentiate x with respect to x, and we get v plus we keep x as a constant and differentiate v, where we get the v dx. Alright, so this is what we get as our equation. So we effect two substitutions, that's equation 1 and then equation 2, into our given differential equation to be able to solve for our general solution. So we take an example. So example, solve dy dx is equal to x squared plus y squared all over 2xy. So clearly we can see that this differential equation is not a linear. We can see this differential equation is not a linear equation, and this cannot be separated, and it is non-separable. So now that it is non-separable, is this homogeneous? Now let's see, dy dx is x squared plus y squared over 2xy. Is this homogeneous? And an easy way to find whether a differential equation is homogeneous is that the terms should all be to the same degree. So when we take x to s squared, it should have the same power as y squared, and that should also have the same power as 2xy. Then we could see that the power here is 2, and then below here we have x, y, see power 1 plus power 1. When we add them, we get 2. So this is homogeneous. Alright, so the differential equation dy dx is homogeneous. We wouldn't have to go through the stress of having to do the lambda x, lambda y. This is an easy way. So this is homogeneous. So now that we know that it's homogeneous, we effect two substitutions where y is equal to vx and then y prime, which is dy dx, is equal to v plus x v on dx. So wherever we come across dy dx, we put in this expression. And whenever we come across y, we put in this expression, star, and then star, star. So now we take our differential equation. So we have it as dy dx is equal to x squared plus y squared all over 2xy. So in place of dy dx, we put a vein plus x the vein dx, and that should be equal to x squared. And in the place of y, we put vein x squared over 2x, and in place of y, we put vein x. That's a simple substitution right there. So we come to this point where we have v plus x dv dx is equal to x squared plus vx squared all over 2x times v of x. Going forward, we have x dv dx is equal to x squared. We factorize x squared out. You can see it is common. It's common between the two expression. There's x squared here and there's x squared here. So we factorize x squared out. We come to a point we have 1 plus v squared all over 2x squared multiplying v, because when we multiply we can get x squared minus v. Remember, we transpose v from this side to the right hand side, so we get minus v. So what we get now is x dividing the x is equal to, this one cancels this, till we come to a point where we have 1 plus v squared over v minus v. So this is our expression now. This is our expression now. We have to simplify the right hand side. So this is what we come to get. We get x dividing x is equal to 1 plus v squared minus v squared all over v. That the LCM is v. And we can see that this one gives us x dividing x is equal to 1 over v. Yes. Yes, so we get this as our expression. Now, we could see that we can easily divide through by the vein so that we group like terms. So in doing so, anyways, a correction right here, we can see that there is a mistake here. So we get x dividing over the x. In simplifying the right hand side, we come to get s equal to 1 minus v squared over 2v. So this is what we get for the right hand side. Because there was 2 there, I didn't bring it here, so there has to be 2 here. So we come to get this, and when we get this, you could see that this has become separable. This differential equation is now separable. You can take a quick look at that. It is now a separable differential equation. We can separate it. And how do we separate that? let's divide through by the vein. So in dividing through by the vein, we come to get x over the x is equal to 1 minus v squared over 2 v the vein. Yes. So we have this as our differential equation. What we have to do is that we can reciprocate it. So when we reciprocate, we get the x on x is equal to 2 v v on 1 minus v squared. That is after reciprocating. That's reciprocating. So after reciprocating, we get that nothing has changed here. We can quickly go ahead and solve our differential equation. Now we have the x on x is equal to 2v v all over 1 minus v squared. This is our differential equation. This is now separable. So what we do now is that we integrate both sides. Take the integral of this and take the integral of that. And when we integrate the x on x, we come to get ln x plus c. When we integrate, we introduce our arbitrary constant plus c. But because a c is an arbitrary constant, I can manipulate it in whichever way. So I bring it plus ln c. Please note that when you integrate 1 out of x, you get ln x. Yes. So that's how come we had ln x here. X equals to the right hand side. Now you can see the right hand side is integral of 2v v for 1 minus v squared. Now we cannot solve the right hand side straight away. We have to solve it by the method of substitution. So we have solving the right hand side, which is integral of 2v v all over 1 minus v squared. We have to solve it by substitution. So now let's u be equal to 1 minus v squared. That is u prime, which is du the v is equal to negative 2v. So this is our equation, and then we proceed. We now have the integral of 2v, that is 2v the v over u. But then mind you, the v from this part, the v is now equal to du over negative 2v. So we effect that here, and then we get integral of 2v over u times du over negative 2v. So what we come to get is that this one cancels that, and then we come to get the integral of negative 1 over u, that is du. So when we get this, we get negative of ln u. So this becomes our final answer. But we know that u is equal to 1 minus v squared. So quickly we do a substitution. But note that whenever we have negative ln of a function, so negative ln of u becomes ln 1 on u. Alright, so we have this as our equation. So substituting u into the equation, we have it to be ln 1 on 1 minus v squared. So this is what we get for our right hand side. Our left hand side has been solved already. So quickly we equate the two. So right hand side should be equal to left hand side. And we know that right hand side we had lane X plus lane C and that is equal to our right hand side. Now right hand side is lane 1 out of 1 minus v squared. Now from logarithms we know that whenever we have lane, as a lane expression plus another lane expression, it becomes a product. So we have this common lane xc is equal to lane 1 minus 1 minus v squared. You know that lane cancels lane, and then we come to the point of xc being equal to 1 out of 1 minus v squared. So now this is what we have as our expression. But then note that y was equal to Vim x, meaning Vim is equal to y on x. Remember the substitution we effected, meaning we have to do that substitution here. So xc becomes 1